Hello, my name is Rikard König and I'm CTO and co-founder of Ekkono Solutions. Ekkono provides an edge machine learning library for embedded applications, and in this session I'm going to talk about how edge machine learning in embedded system can enable decision support for IoT. But let's start from the beginning and why traditional machine learning sometimes struggles or even fails. Of course, there is not an either-or. Some use cases are better done with a centralized approach in the cloud, while others are more suited for a decentralized approach at the edge. The traditional approach is based on the assumption that we have a set of similar devices which we can learn from by analyzing their data. Let's say that we, for example, want to do range prediction based on the fuel consumption for a fleet of trucks. This sounds like a reasonable idea, but in reality it's however not so easy, since the trucks will be used in various environments and we have different configuration that may even change over time. Just making it possible to collect all relevant data could be a showstopper. On top of that, you might be dealing with a flaky or very limited internet connection, or that you are not allowed to send data to the cloud due to security or integrity reasons. In this situation, a decentralized approach using edge machine learning will really shine. By creating one model per device and training it on board the device, you don't need to send all the data to the cloud, and you don't need to explain how a device differs from another. You don't even need to collect data explaining the differences between devices and their environments. The challenge is, of course, to enable machine learning on the edge devices, which are typically very constrained in relation to the CPU and memory resources. A key then to enabling machine learning is incremental learning, which differs from typical machine learning approaches by continuously training the model as data becomes available, instead of training it once on a large previously collected dataset. Incremental learning is a slightly harder problem since we don't know which values we are going to see. But on the other hand, we can start making rough predictions directly based on what we know so far and continuously learn and improve the model along the way. At the same time, the computations are distributed over time, which avoids computational bottlenecks. Because of these reasons, incremental learning really is the key in edge machine learning. So, how do Ekkono fit into this picture? Well, Ekkono provides a machine learning library that is designed to be used on these edge devices and their embedded applications. Let's start with an example. Imagine that we have a heavy piece of machinery with some wear part that is gradually worn down. Here we will take the example of a stone crusher, which is used in mines and on construction sites. Naturally, the crusher is under heavy wear and the mantle that the stone are crushed against are gradually worn down and eventually need to be replaced. However, the frequency for how often the mantle needs to be replaced depends on the hardness and density of the materials it is crushing and how hard the machine is run. The density of the material differs between sites and even over time and cannot be measured in a practical way. Here it becomes interesting, and a centralized approach would struggle since the wear would differ greatly among sites. We have full control over the operation of the machine, but we cannot estimate the density of the material and thereby the wear. Now, let's assume that we have 4 sites, A, B, C, and D, which all have different stone material. And these charts show how the wear, in dark green, defined as the remaining mantle thickness, varies among the sites depending on the density of the crushed material, depicted in orange, and the power usage depicted in red. Note that the density fluctuates and that the mantle used in site A lasts almost twice the time compared to site D. Now let's look at how we would tackle this problem with a centralized approach. First of all, we will need to upload the data related to the wear and power consumption to the cloud from each site. This is often easier said than done, especially from remote mining sites. But let's say that we have been able to upload all the data to the cloud, then the next step is to build a model that can predict how much time and power we can still get out of a particular machine before the mantle needs to be replaced. Here we would run into problems since the density of the material varies between the sites and since we cannot measure it. Thus, there is no way to account for the wear in the cloud, and the best way what we can do is to estimate an average wear, given that we have previously gathered statistics on that. And these charts again show the wear in dark green, but here the red line depicts the accumulated power used over time. And finally, the light green horizontal line is the prediction of the total power consumption that the centralized model would give. That is the observed average previously changed mantle.
If the prediction of the accumulated power consumption meet at the same point when the wear reaches zero, the prediction is perfect, and that is the predicted total power you can get out of a mantle is a perfect match with the actual power consumption and the time you got out from your mantle. And looking at these charts, we can see that the prediction is rather good for site B and C, while A could run much longer than predicted and site C significantly shorter. Obviously, this is not a good enough solution. If we instead turn to a decentralized edge machine learning approach, we would instead construct one model per crusher, and the model would consume the sensor reading and make the predictions without needing to send data to the cloud. And by using incremental learning, we would avoid the need of first collecting a large data set, while also enabling adaptation of the model if the crusher would be moved to a new site, or if the density of the material would change. Here, the charts show the results of applying this detailed decentralized approach to the same problem. Again, the light green line is the predicted total power consumption, and the red line is the actual accumulated power consumption. First, we can note that the error between the predicted total power consumption and the actual accumulated consumption is almost zero. Secondly, the prediction is no longer a horizontal straight line, but varies, which is due to the incremental learning. The prediction fluctuates the most in the beginning, since the model only has seen a few data points, which themselves contains both noise and variation. However, it only takes around 100 points until the model finds the general pattern and the prediction is stabilized. In the last half of the mantle life, where an accurate prediction is the most important, the predictions are stable and very accurate. So even if we don't know the conditions of the stone at each site, we can still make very accurate predictions since it's not changing. But what would happen if a change in stone density occurred during the lifetime of a mantle? Well, let's assume that it does, and it changed to a much higher density of the material. And we can see this depicted in the charts for site E and F. And here it's easy to see that the higher density affects the wear as it gives the light green wear line a steeper angle after the change. However, since we're using incremental learning and continuously adapting, the model automatically accounts for the change. Naturally, it's not possible to predict the shorter lifetime beforehand since the change was unknown. But after only a few new data points, the model have been retrained and given a new accurate predictions again. Okay, so that was an example, and now let's look at a real case we started in August this year with the British medtech company Peninsula Medical Technology, or PenMed. They focus on the field of critical care and anesthesia with the development of an anesthesia machine and ICU ventilator. PenMed combines the experience and expertise of clinical end users and the power with machine learning. In this case, they wanted to explore how Ekkono's library could be used in a new approach for optimizing the treatment of patients in emergency care using machine learning. When PenMed presented the idea of a smart and more personalized approach using edge machine learning, we tailored the machine learning solution even more with our unique incremental learning method. It's really the same approach we just looked at with the stone crusher, but applied to patients and ventilators. The project is still ongoing, but the results so far are groundbreaking, and the plan is to get the product to market. So what have we learned? Well, the point of this example was to demonstrate how a decentralized edge machine learning approach can solve problems that a traditional centralized approach cannot. We saw that the environmental factors that differ between devices can be ignored if you create one model per device. Even when a new model was trained from scratch, it was significantly more accurate than a centralized approach and very accurate at the end of the lifetime of the device. Finally, we also saw that incremental learning enables adaptation to changes in the environment. And the approach taken here holds for most applications of remaining useful life, where individual usage or environmental factors affect the life of the device. It also extends to most predictive maintenance use cases and even optimizations that must be done on an individual level. And until today, a product has been at its best when it has left the factory. But with incremental learning on the edge, they can become better and more optimized for their specific usage the more time they are used. And the key is to divide the problem into smaller parts by making one model per device and to use incremental learning to adapt to changes and to make it feasible to run machine learning on the devices themselves. Well, that was all. To find out more about Ekkono and how we can help you to make your product smart, please visit our website, ekkono.ai.